audible properly?
Yes, you are audible.
What do you see? Can you confirm?
Yes, we can see aspects of imaging, lecture 5.
Okay, so all right, let us start. So we have already assumed, or at this point we already have done, what we have already done is that we say that we have completely calibrated uh, the visibilities. So what I write as observed visibility here is the best visibility that you can achieve after calibration. There will be some noise left all the time, but that is the best that you can do. So that is what I am assuming. And all the gains are now 1. And you know that now I can write this as a function of u because the gain is over. So this doesn't depend on the antenna anymore. It only depends on the baseline. So this is the expression. Alternatively, which you can also write, and you can see that I have put in the frequency dependence, which now I write as nu instead of omega, which I was doing earlier, but they are same thing. Alternatively, I can also write it in the component form in the coordinate system of our choice, which we have discussed many times. And this is how it will look like. Remember that these integrals are from -1 to +1. What you have not still done at this point is this visibility is still not the Fourier transform of the sky brightness distribution. If we can, for the time being, neglect the W term and this root over of 1 minus L square minus N square here, consider small field of view. If we do all of these, still it is not Fourier transform of the sky brightness distribution. What else is sitting in between is this trivial antenna response. So if I really want to write down the observed visibility, I can write it in terms of the visibility which is related to the sky, which is only related to the sky brightness distribution, as a convolution of that with a Fourier transform of the antenna beam pattern. Okay, is this clear? Is there any doubt? How do I write this expression? I have this where I and A, if I, for the time being, consider this as a Fourier transform relation, it's a multiplication of I and A and then doing the Fourier transform. Once I go to the Fourier plane, which is the UV plane here, that multiplication becomes a convolution of the Fourier transform of the individuals being the sky brightness distribution, Fourier transform of that is this, and the antenna beam pattern Fourier transform is here. Okay, what is the meaning of this? It means that this function, which is the Fourier transform of the antenna beam pattern, because the antenna beam pattern has a finite extent, this will also have a finite extent. We know from the Fourier transform theory that in one plane, if it has a finite extent of θ0, like for the antenna beam pattern, θ0 is say the field of view, then in the Fourier plane, this A tilde will have a finite extent of 1 by θ0. And you know θ0 is lambda by d, 1 by θ0 is d by lambda. So this Fourier transform kernel has a finite extent of d by lambda. That means that my information from the sky has got converted at the scale of d by lambda. I don't have any individual information, any independent information in the baseline plane at a scale less than d by lambda. Okay, so is this point clear? This is what we will be using for next 15 minutes. So let me know if this point clear, if there is any doubt at this stage. So in the baseline plane, I don't have any independent, if I choose two baselines which are as close as d by lambda or closer, I will not get any independent information from these two baselines about the sky. which means now I have a maximum baseline, which I call, say, Umax. Corresponding to that, I have certain spread in my U, V, and W. Beyond that, I don't have any measurement of the visibilities. I also have a minimum baseline. Smaller than that, I don't have any independent information. So the maximum amount of information that you can get out of this is Umax divided by delta U, cube of that. I said maximum if you have measured at each and every position in the baseline up to Umax at an interval of delta U. Okay, then this is the maximum amount of information that you will get. Now, for each visibility measurement, there is also a noise associated with it. Poonam has showed you this expression for the noise. Let me show you again. The noise in each visibility depends on the source equivalent flux density of the instrument. And in this case of in the case of small frequency, low frequency observation, it's also major part of it comes from the sky. So SCFD is nothing but the total system temperature divided by the gain of the antenna. And then in the denominator, you have the width of each frequency channel where the visibility is measured and the time integration over which the visibility is measured. Remember that we have discretized the visibilities in time also, and the delta T is that time interval. So this is the noise. And as you can see that if I increase delta nu or increase delta T, I will have less and less noise in each visibility. So just let me remind you, that is the noise term which is coming with each visibility. And it is important to have lesser noise because remember that your gain solutions that you have got, you are doing kind of chi-square estimation for the gain solution. And you know that chi-square estimation is better and better if you have lesser and lesser noise. So in principle, I would try to increase delta nu and delta T. I'll try to integrate for larger time and integrate for larger frequencies. The question is, can I do so? Should I be able to integrate for as high time as I want, time interval as I want, or as large frequency as I want? The answer is no for both cases. And let us see roughly why that is the case. This derivation or expressions are not exact. There are certain things which are completely ignored, but this take home the basic idea. So what have we done here? Remember that if I consider a baseline, that is nothing but the difference in the antenna separation between two antennas, say XA and XB or X1 and X2, in terms of the observing wavelength. So I can as well write that delta X by C times nu. Now, the difference in the antenna separation, this delta X vector, never changes whatever you do. The component of this vector will change if the direction of the sky in which you are looking at will change. But this delta X vector itself will not change. But U will change if I change the frequency. Lambda is nu by C, lambda is C by nu. So it will change if I change the frequency. So if I choose a bandwidth of delta nu, U directly linearly depends on nu. And I think that C does not change as well as your light is traveling in free space. Whatever you do, C does not change, that special relativity. So the delta nu bandwidth will give you a range in delta U, which is given by this. Delta X by C into delta nu, just coming from the previous expression. So if I choose a bandwidth of delta nu, then that will correspond to a spread in the baseline, which is delta U given by this. Which direction this spread will be? Well, this spread will be in the radial direction in the baseline plane. Why? Because you see, if I consider the vector x1 minus x2 in the baseline plane, let me try to draw one here. So say this is the vector in the baseline plane. The amplitude of this vector is delta x by c into nu. And if I change nu, the amplitude of this vector will change, right? So this spread in the frequency will give you a spread in the baseline in the radial direction for each baseline. If the baseline is pointing to a different point, the baseline vector is pointing to a different point in the baseline plane, it will get stretched or shrink in that direction if you change nu. All right. So that gives me a radial extension. To ask the question that what is the maximum radial extension possible, you can show that that will happen for the maximum baseline that you have. Is simply because this delta x is fixed and delta x max is also fixed. If you are working with GMRT, delta x max is 25 kilometer. So that is fixed. So there should be delta x max by lambda here, not c. But if you work it out, you will see that the maximum radial extent that you will get for a frequency delta nu is u max times delta nu by nu, which you can also call the fractional channel width. Fractional because channel width divided by the frequency of observation. Now this, if I make it large enough, I may at some point hit that delta u, which is d by lambda. If I make it even larger, obviously I will miss some information about the sky. If I make it smaller than d by lambda, then it is all right. So the delta nu, which is the width of each channel over which you are measuring the visibility, can at max be this, determined by this relation. And because of that, this delta nu cannot be smaller enough anymore. So each visibility will be limited by that much of noise. So this, if you see the fractional channel width, depends on the ratio of the antenna diameter to the maximum distance between the two antennas. All right. So if you have any question at this point, please ask. This effect is called bandwidth smearing. If you don't respect this expression, make delta nu larger, then you get a smearing of the sources in the radial direction. If you make an image with such visibilities, it's called bandwidth smearing. So if you have any question at this point, please ask, then I will proceed. Shuman, is it still noisy because of the fan?
No, it's fine.
It's fine.
So you are host now. Can you just transfer that? I cannot control anything from here.
What should I control?
No, you just make me host.
Oh, acha, I want to make you host. Okay, Shuman Chatterjee, mode. Make co-host.
Make host.
So how do I make host? Shuman Chatterjee, mode. Make host. Okay. Change host.
Thank you.
Okay. You have been hosted to host. Okay. So if there is no question at this,
I had a question. So
yeah, please go ahead.
Explain means like how does our experiments being affected by this bandwidth smearing once more?
Yeah. So what you are getting here, if I have bandwidth smearing, what you will do is the following. You are supposed to, you will assume that you have independent information at delta u, right? But you will not have. Instead of having independent information at delta u, your independent information will be in a rather radially elongated line. So if I break in amplitude and phi, the amplitude of the vector and the angle, to 2D polar coordinate. So my information, independent informations now along this radially elongated lines. Not only that, that radially elongated line has a larger width. If you go to the edge of the baseline, if your baseline is smaller, if you are closer to the u equals to 0, then that effect is lesser, right? Because it depends on delta x or this u. So now if I want to do the Fourier, once I do the Fourier transform of this, see the Fourier transform preserves the information in different axes, right? So if I have something radially elongated in u, I will get that radially elongated in the Fourier domain also. So in the image, you will see the point sources which are far from the center will have radial elongations, more radial elongation. Near to it, the center have less radial elongation.
Okay.
Okay. So now let us ask the following question. So this gives you a radial elongation, right? What about the direction along the angle? Okay. So let's ask the question how the baseline components changes with time. So let me remind you that the baseline vector you can write in the direction cosines Lm and n, square and add, you'll get 1. And the, sorry, not the baseline vector, the unit vector along the direction of a particular point in your source. Your baseline vector is also written in terms of the u, v, w coordinates, which are the projection of u along this different, along the same coordinate system. Okay, but this u is also the separation of the two antenna pairs in the physical units, so in kilometers, in terms of observing wavelength. Now this separation of the two antenna pairs never changes. The antennas don't shift their position, so the separation never changes. If I fix the frequency of observation or the wavelength of observation, lambda also never changes, which means the amplitude. So if I fix two antennas and observing at a single frequency, the amplitude of the vector u for these two antennas will never change. The components u, v, w will change. The vector property of u will change, but its amplitude will never change. So if I now ask you the question that where the tip of this vector will lie in 3 dimension, it will has to lie in a sphere because the radius, which is the magnitude of this vector, is constant, right? So you realize that as the time progresses, the tip of the baseline vector lies in a sphere. You also know that these components depends on which direction you are looking at. Maybe there is a source in that direction. And roughly speaking, after one day, a source will almost come back to the same direction in the sky. Which means that this tip of the vector not only has to move in the sky, in a sphere, on the surface of a sphere, it also has to make a complete circle on the surface of a sphere. The circles may be a great circle, may not be a great circle, but it has to make a circle on the sphere. Now, if it makes a circle, and now if I look at the projection of that circle in the u and v plane, which is what Arnav was showing you from the morning many times. He has shown you many such examples. All of these projection of circle on an arbitrary plane is always an ellipse. So you'll always see ellipses in the projection. Okay, now this can be rigorously proved, and depending on the latitude of your telescope and the declination of your source, you can see what is the center of the ellipse, what is the ellipticity, what is the radius of the ellipse, same major axis, etc. But I'm not going to the proof for this lecture. Now, let's say that my baseline, the maximum baseline is Umax, and the time interval that I've chosen between observation is delta t. Then in 24 hours, the Umax vector, the vector Umax comes back to the same position, right? So let's remember these three things. And let us assume that what I said, that the baseline vector make an ellipse. If I look at the UV plane, let's assume for simplicity that it's a circle. The ellipse is actually a circle with a radius of Umax. Now you can see now that it has to move circumference 2 pi Umax in 24 hours. So roughly speaking, apart from a factor of 2 pi, in every delta t time, it will move by this amount in the azimuth direction. So this essentially gives you, just like we saw a radial extension for the bandwidth smearing, this gives you an azimuthal extension. And if you make this delta t large enough that this delta u phi is now greater than d by lambda, the smallest independent element that you can get in your baseline plane, then you will get a time with smearing. Okay, so again, I will stop here and let me ask you if you have any question. So what we realized here is, you can still ask the question. I'm just carrying on with what I was trying to make here, the points, that I cannot make this delta nu arbitrarily large. I cannot make this delta t arbitrarily large. There is a physical scale for both delta nu and delta t. I cannot go beyond that. So my visibilities will have a finite noise always. Yeah, so if you have any question, please ask. Otherwise, we will proceed. Okay, so seems that there is no question, or you got all bored already. So let us proceed, or let me proceed. What we'll discuss, the things that we'll discuss for the rest of the time, rest of my time, is that what are the different problems in imaging techniques. I am not going to talk to you much about how to do the deconvolution and how to do imaging also, making different grids, etc. Those Poonam has talked to you about, and if you really want to know about those more, we can discuss it later. But let's discuss further problems that are really more relevant with, and some techniques which are more relevant regard to the low frequency observations, like for LOA. First of all, we do not measure this point. Also, you already know about this point, but let me emphasize again that we do not have measurements at every point in that box that we are talking about, which has U, V, and W going from minus Umax to plus Umax. And the minimum separation that you can think about is capital D by lambda, which we call delta U. This entire grid, if you wish, three-dimensional grid, is not filled up while you are doing observation. You only have filled up some of these grid points. Some of the grid points given if your antenna pair has visited that point at any time during your observation. And that is what we call sampling. And the sampling function is usually written this way. If that grid is filled, you call that UI grid is filled. So that's why there is a delta function. And obviously there are many measurements. So I goes above all the measurements. So what is the problem with incomplete baseline sampling, something that you have already learned, but let me repeat it again. If I have the true visibility, which is a function of u, it's not a sampled function of u, it's known at every baseline point, then that is kind of some type of transform of this I times A. But the sampled visibility is the same thing that was sitting here, but now multiplied by the sampling function. If I call the Fourier transform of this entire thing as ILM, then what do I have if I do the Fourier transform of the sampling function? Well, now it is a multiplication in the baseline plane. So I get a convolution in the image plane. When I say baseline plane, it means that some function is given as a function of u. When I say image plane, some function is given as a function of lmn or n cap. So it's a convolution of this I, which is a true sky brightness distribution. I should multiply it with A also, but forget about that for the time being. And then convolve with the Fourier transform of the sampling function, which I have defined here. It's called the Darty beam. This behaves like the beam of the interferometer. You know that whatever is the source in the sky, whenever you have an optical instrument which is observing it, the intensity pattern that you get out of the optical instrument is the source in the sky, intensity distribution in the sky convolved with the beam of the optical instrument. This is, in this case, the Darty beam is the interferometer beam. So I need to deconvolve this if I want to get back I. Now, as Poonam also pointing out earlier, you don't have measurements at all the baseline plane or baseline grid. I should say baseline grid because it's really U, V, and W. It's a three-dimensional entity. I don't have measurement everywhere there. Where I don't have measurement, I have zero measurements. The values are zero there. Because of that, if I really want to do deconvolution, that amounts to interpolating the values of the visibilities where it is not measured. And that's a very important point, because imagine that I have, let me draw for you here. Imagine I have these three adjacent baseline grids, and the measurement is done here, the measurement is done here, the measurement is not done here. So it is not sampled at the central box. So to do the deconvolution, one can mathematically prove that you have to interpolate somehow in the box in between. Now, how you do that interpolation, your image will completely depend on that. So as I have written, you can interpolate with a fish in the box where you have not measured. So your image will be fishy. If you interpolate with an elephant, the image can resemble an elephant. So the basic point is that how you do this interpolation, how you kind of fill up the baseline points where the visibilities are not measured, your image depends on that. So that means if I now use this image to find out the structures in the image at different scales, which essentially is the power spectrum of the image, and remember that it is the power spectrum that we wanted to measure, that power spectrum will not give you the true power spectrum, because by doing these interpolations, I have actually changed the scale dependent properties in my sky. Okay, that's a very crucial point, because you may think that I'll make a very good image and I calculate the power spectrum from it. There is absolutely no guarantee that you will not do a mistake. And there is guarantee to some quite good extent that you will do a mistake. You will make a wrong power spectrum estimate. It's not only that, it's even more severe. What this interpolation also does is that it interpolates not only the visibilities at those intermediate points, it also interpolates the noise in the visibilities at those intermediate points. Remember, I had 3 grid points and the center one, I did not have any measurement. The noise in the 2 boxes in the 2 sides of the center one were completely independent. But when you interpolate the visibilities at the center, you are also interpolating the noise. And that noise is now correlated with either sides of the boxes. So the interpolation also interpolates the noise, which means that this deconvolution procedure essentially gives you different noise and the different parts of your image plane. If you calculate a power spectrum now from the image, it only not changes the power spectrum because you have interpolated the visibilities. It also adds a noise power spectrum to it. So it completely changed the power spectrum. And we worked on it and we demonstrated that it is quite the effect. So let me show you this image, this picture, where what we had done is that we have chosen a mock image, and this mock image is absolutely has nothing to do with EOR or anything else. But this is just to demonstrate what happens if you blindly use the image to get the power spectrum. Okay. So I have chosen a mock sky. Yes, any question?
Yeah. So yeah, I had a the visibilities are usually random, right? So when you interpolate,
the noise in the visibilities are random. Visibilities has some structure, right? See, visibilities has some correlation at different length scale. That is a power spectrum. Visibility.
Right. Yeah. Right. It is, but when you interpolate, you introduce extra correlation, right?
Right. No. When you interpolate, it introduces extra correlation in visibility. It also introduces extra correlation in noise. It does 2 things.
Yes.
Yeah.
But it's just something I was wondering. So, but do you expect your visibilities to be smoothly interpolated along the baselines?
No, I don't. I don't want to.
Because that will, when you take Fourier transform, that will create some funny structure in the image plane.
Right. See, the point is that what you want to know. If you want to know the scale structures in the sky, then you should not make an image and find the scale structure from there. If you want to know how your image looks, how your source looks in the sky, I don't think that we don't have a good processing power in our head to look at the visibility and figure out how the source should look in the sky. So then you have to make an image, right? So it again depends on what you want to do. So this picture demonstrated. So this black line is the model, which is something that I have simulated as the sky distribution. And I know the power spectrum of it. That power spectrum of that is, or the visibility correlation, which Samir will discuss, the scale structure, whatever you call it. Don't bother about what this represents for the time being, but that black line is a true thing. And once I calculate it directly from the visibility without making a noise, I get the pentagons, which all sits on top of the black line. And then I have 3 different ways of estimating the image, and I don't want to go to what are they. But you see that the power spectrum calculated from these 3 different ways of estimating the image, the blue, the circles, the squares, and the triangles, none of them follow the black line. So if I use the image to estimate the scale structure in the sky, I am gone. I will do something. I will estimate something which doesn't represent the sky.
those which U, R, and N.
I don't want to go into that, but if you really want, they
Okay,
are
okay.
different weighting schemes.
Okay,
Uniform,
okay.
random, and natural. Sorry,
Okay.
some Briggs and natural. Okay. Now, remember that when I talk about, so far all the discussions that we are talking about, we just pick up two antennas and see the visibilities of these two antennas. And if I choose one of these delta U into delta U cell in the baseline plane, in the UVW, not the baseline plane, the baseline grid, UVW grid, then I will have, may have a contribution, a measurement from this pair of baseline. This pair of antenna. But I may have another pair of antenna at a different time, giving contribution in the same baseline grid, right? So now I have to consider both the and I have to figure out that how to combine these two measurements to give a representative value of the visibility at that given grid. Okay, so that is done by weighting and grading schemes, which Poonam has talked to you about length, and I will not go into. Am I there? Hello?
Yes. Yes.
Yeah.
Yes.
So no, it showed that your internet connection is lost. That's it. Okay. So you have to do this gridding and weighting in such a way such that you you reduce the noise, you do an appropriate, you get an appropriate resolution for your science case, and you don't have aliasing. And this Poonam has discussed about different types of weighting schemes and tapering schemes, and I will not go into the details of this. So what I will talk about next are the problems of mostly the clean algorithm. Okay. So what we have already discussed is that we have an incomplete baseline coverage. So most of the places in this three-dimensional grid in the UVW is empty. And that creates a problem that we have already discussed. Any deconvolution algorithm will have that problem. So do clean. And we'll talk about a multi-frequency synthesis, which Arnav showed you some picture of it. And what is the basic idea that we'll talk about shortly. But remember that clean itself also does try to represent the sky as a collection of point sources. Now, the sky may be a collection of point sources only, then this is a very good representation. And actually, when you say point sources, remember that at the last step of clean, you use the clean component, convert them with a Gaussian, and then that is how you produce the image. So you really don't use, you don't represent the sky in terms of point sources. You represent the sky in terms of narrow Gaussians. The width of the Gaussian is the synthesized beam of your interferometry. What is the problem in there? Now it turns out this is again can be shown mathematically rigorously that if I give you a two-dimensional function of xy, just like the sky, the intensity distribution in the sky, no two-dimensional function or one-dimensional or any dimensional function can be uniquely written in terms of Gaussian basis or the clean beam basis if you wish. And that you should already know if you have done the harmonic oscillator problem, because you know the harmonic oscillator wave function, the basis of the harmonic oscillator wave function are Gauss-Hermite polynomials. So what's a good basis is a Gauss-Hermite basis using which you can represent any function. But if it's only Gaussians, you cannot do that. So definitely there is a problem. You are trying to break down, you are trying to write your sky as a linear combination of in a basis which doesn't work as a basis. So one way of do a better approximation is what Arnav talked about. It's called multi-scale synthesis or multi-scale imaging, where instead of choosing a single width Gaussian, you choose multi-width Gaussian. Even today, there exist algorithms where people use a basis called shapelet basis, which is based on Gauss-Hermite polynomials. So you represent the sky in terms of a collection of Gauss-Hermite polynomials. Why do you want to represent in terms of Gaussian basis only? Well, if you are representing in terms of Gaussian basis, you have to tell what is the intensity of the source and the position of the source, nothing else. If it is a complicated like Gauss-Hermite basis, you need to give more parameters. So that becomes obviously more computationally extensive. So clearly, the first approximation of clean has a problem, and you should address this problem. Even if you have, even if you have complete baseline coverage, if you have complete baseline coverage means that all the points in this 3D grid is filled up, you don't need to do reconvolution anymore, right? So then you don't need clean anymore. But otherwise, this problem remains. Most of the interferometers also have a smaller baseline cutoff. So it cannot measure lower than a certain baseline. Okay, so there is a maximum baseline up to which you can observe, but there is also a smaller baseline which makes a hole at the center of the baseline plane, or makes a circular hole in the center of the baseline grid. Remember that smaller baselines measure the larger scale structure in the sky. So we talked about this structure called the diffuse galactic synchrotron radiation, which exists everywhere in the sky in the field of view, which means that structure is mostly present at those smaller baselines where you have zero sample because there is a hole in the baseline. It's not that some point it is absent, it's not present anywhere within a smaller U. So you completely miss the large scale structure because of that. And then the Vansittart-Zernike theorem is not quite a Fourier transform relation. So how to invert from the visibility to the image for large values of this W term and large field of view, that is also a problem, right? So these are the problems of the clean algorithm. Some are of any deconvolution algorithm and some are particularly of clean. So if you have any question at this point, please let me know. And after that, I will proceed. Okay. Okay. So let us discuss about this idea which we call the multi-frequency synthesis. Okay. So what was the problem that multi-frequency synthesis was trying to address to solve? The problem is that we have incomplete coverage in the baseline plane. And let us call it baseline plane for the time being. Let us say that all W's are 0 or certain value, just for simplicity. So I don't have sampling everywhere in the baseline plane. Now, if my source does not have any frequency structure, which means my source looks exactly the same along my bandwidth of observation, then what I can do is I have the visibilities as a function of L, N, and nu. Let me go back to my first slide here. I have the visibilities as a function of, U let me come here, u and nu measured at different u and different nu. But if my source doesn't have any frequency dependence, then you get extra information from different channels, because all the channels now have the same information about the source, which is I as a function of n cap only, not a frequency dependence, right? So if a source doesn't have any frequency dependence, then I can actually combine the visibilities observed at different channels. You see, I cannot make the channel smaller, because then I will have the bandwidth smearing, as we discussed here. But while making the image, I can do some clever transform, which will actually let me get more information of the visibility plane, more measurements in the visibility plane. Why more measurement? Because then every frequency will measure at a little different baseline shifted in the radial direction. Now this Arnav showed you that the baseline gets shifted in the radial direction if you use this information. So one uses that while doing the multi-frequency synthesis. So let us ask the question, how do I do that? And as I said, this is only possible if your source is only a function of, is not a function of frequency. So what I can do is, whatever my source be, I can now break that source. I can essentially tell or expand that source in frequency. How do I do that? Well, for most of the foreground sources that we discussed, they are kind of synchrotron radiation, which means the intensity at a given frequency from a given point for each pixel in the image can be written this way. It changes with the frequency just like a power law. Now, in principle, for different pixels or different sources, this power law can also depend on which point in the image you are looking at. So this second expression is nothing but the first expression written in a different way. So what I can do now is I can tailor expand my source in frequency like the following. So this is my source, which actually depends on frequency. I write that in terms of a frequency dependent component. So this is basically the intensity at certain frequency mu0. And then the first term, if I can just keep one tailored expand term, the first term will be alpha, which also depends on different position in the sky. And then this term, which is just a frequency factor. If you want, you can keep higher terms. Arnav was talking about order terms as well. But now if you look at this I, which is a function of frequency, can be written in terms of two quantities, I lm nu naught and alpha lm. None of them depends on frequency. So I can make, in my VCZ theorem, I can break I in these terms, and then I have to make image of ILM nu0, and I have to make image of ILM, alpha LM. I have to make two images instead of one. If I keep higher order terms, I have to make one more image if I keep one more higher order term. But each of these images are independent of frequency. So I can use information at different channels to make each of these images. So instead of making only one image, I make several images depending on how many orders I want to keep. But then I can use all the channels to make each of these images, and I have a better baseline coverage. So I improve on the baseline coverage doing this. So this is the basic idea of multi-frequency synthesis. So again,
but
if you
how
have,
do you image this alpha LN? Because the where your cursor is, that shows that it is frequency dependent. No,
no, this alpha is not frequency dependent.
I understand, but you have written the equation in a different manner, just above that, right?
Here, where is the frequency dependent here? No, this nu you are talking about?
Right.
No, but this nu is, you can take it out of the integral, right? This nu is not a L and M dependent. There's no image of nu. See,
Right.
Let me-
No, I understand.
let me go back here. So instead of I here, I have to write I plus some A times alpha. That I and A is nu, not nu dependent. I can multiply this entire expression by nu. That doesn't do any harm, right?
Right.
Okay. Any other question? Okay. So let us now take up the other challenge in imaging. It's not actually deconvolution challenge. This is an imaging challenge, which is the Fourier transform problem. The fact that the Van-Sitter-Zernike theorem is not quite a Fourier transform relation. Okay, so let us ask the question, how one address that? Now, if you really look at this expression, you realize that it's not that just this is not a Fourier transform relation. There is something more not going on right in terms of if you want to look this in terms of Fourier transform. What is not going right? Well, what this is doing is mapping a function, which is ILM, which is on the surface of a sphere. This function is a function of two variables, L and M. And the VCZ theorem is mapping it to a function which is visibility, function of now three variables, U, V, and W. And these three variables in our choice, they're in a Cartesian grid, right? So this is a completely non-trivial mapping. I mean, if you look at it this way, there is no relation of this with Fourier transform. If I talk about Fourier transform, a Fourier transform is a mapping of a two-dimensional flat plane to a two-dimensional flat plane. Flat means Euclidean. Here, one plane is not flat, and the mapping is from 2D to 3D. Okay, so this should ring a bell very loud to you, and you should see what can we do. So here I have depicted what I want to show, that sometimes the field of view may be just above your head, or sometimes the field of view may be here in the sky, which is the hemisphere. And that is where your intensity is defined. So your N0 may be looking at different directions at different times. And this box is the baseline plane. This blue box is the UVW or baseline grid rather, where you have the measurements in 3D. Okay, so that is that mapping you are trying to address. So now, how do I change this? I mean, okay, so it's not a very trivial problem. If I want to inverse this mapping, see, for one case, you have to go from 3 to 2, 3 numbers function to 2 numbers function, and it's not quite a Fourier transform, which is what one want to use, because see, anyway, all your algorithms will use FFT, first Fourier transform, and that is much better and much faster than anything else that you can think of. So the first approximation you do is the following. You say, I am trying to look at this hemisphere, which I have drawn like a circle here. You can think of it as a projection. And I break this up in terms of polyhedrals. So like, if I'm looking at this, so I say that, okay, so this is my, in this black arc is my entire field of view, but that now I have broken up into 3 different small field of views, which I call subfields. And I imagine that I am looking at the center of this subfield, and I project my sky on a tangent plane there. So what problem is solved? I'm not now anymore for that subfield on the surface of a sphere. I am on a 2-dimensional Euclidean plane. So that problem is solved. And if you say that this is much smaller than we have seen in one approximation, the effect of W term is negligible. So let us neglect the effect of W term for the time being. So what I can do now is that I can make an image of this small patch, forgetting about this 1 by root over 1 minus L square minus M square, which is an artifact from the fact that your ILM lies in a sky, in the surface of a sphere, and forgetting the effect of this term also. So then it is a Fourier transform. Now to do this, what you have to do, you have this entire thing as your field of view. Remember that if I want to change the direction, if I have a point source, for example, not at the phase center, but somewhere else, that amounts to a certain phase in the visibility, right? So last time we discussed this, I don't have the slide now, but it amounts for a certain phase in the visibility if you are looking at a different directions other than the direction of your phase center. So what you do is, when you shift your phase center to this polyhedral, or sometimes these are also called facets, to this facet, you add the appropriate phase to your visibilities. Once you do that, you get the visibilities as if you were observing this as the phase center or the center of the field of view. And you make an image, and you make an image separately for this. You do the same thing and make an image separately for this, and then you later combine these images. So that solves the problem that you are not making a transformation from a plain sky, but from the surface, inner surface of a sphere. But that doesn't solve the problem of the W term quite well. Actually, if you really want to keep the W projection, it should be small W projection. I started with a capital W, I kept it. Then you have to be more careful. Even for this small facet, I still have a three-dimensional box over here where the measurements are done. And let's ask the question that what that three-dimensional box measurement does. So what I have done here, I have written the visibilities multiplied by this excess term. And in the right-hand side, I have already done the small field of view approximation. So I'm already doing the faceting or the polyhedral imaging. But in addition, I have kept the excess term here, which was root over 1 minus L square plus M square times W. But that, because still the field of view is small, instead of approximating root over 1 minus L square minus M square to 1, I'm approximating it to be 1 minus L square plus M square by 2. So I'm keeping the next order in the Taylor expansion. And I am, because this term I have added in the left-hand side because I wanted to add in the right-hand side, which will take care of that 1. So what I will be left with is e to the power minus L square plus M square into I pi W. And that I call this G, which is a function of L, M, and W. So I can write this now as a multiplication of A times I, which is always there, times this G, which is a function of L, M, and W. And then I have only the Fourier transform kernel. So this quantity in the left is now actually a Fourier transform of A, I, and G. And it's a Fourier transform of A, I times G. So I can write it as a convolution of the Fourier transform of AI times the convolution and the Fourier transform of G, which I write as G tilde. Now from L and M, I have gone to the Fourier transform space. So this has become U and V. So G tilde is a function of U, V, and W. Now, if you look at it carefully, if I put W equals to 0, then G, L, M, W is 1 because it is e to the power 0. So this term without G is nothing but U, V, and 0. What does it mean? Means the following. I have this chi polyhedral from where the intensity is originated. And this is the pillbox, or this is the cylinder over which my antennas are distributed, where I am doing the measurements. This should not be antenna positions, but baseline positions where I'm doing the measurements. So if I consider a plane parallel to the sky with respect to this, remember that W is something that changes at the direction of the phase center. So in this direction, the W is 0. So now this visibility, which is at UV and 0, if I choose W equals to 0 in this plane, then this visibility is UV 0 are measured here. If I had all my antennas at this plane or the baseline at this plane, then that will be the measured visibility. I would not have any W term. But my antennas are somewhere here or somewhere here. What it amounts to is a propagation of that electric field, which I could have measured here if the antenna was here, to there, or the propagation from here if I'm measuring here, so then from there to there. So this extra propagations, and this extra propagation is by W. So that is this kernel. So this G is nothing but the effect of that extra propagation. So what I can do is, this has become a plane. Now from all the measurements in this box, I can propagate them back or project them into this plane, which is parallel to the sky. And now between this plane and that plane, I have a perfect Fourier transform relation. This plane I have this V, and that plane I have ILM. So that is essentially the idea of W projection. So what is done is the following. So you make facets or polyhedral images. So work on different facets. For each field of view, you first grid the data in UVW. So you grid the data inside that box and then project it into that plane. And that projection is by using this expression, right? So if you want to get this expression, this function, given this function and G tilde. So it's essentially a deconvolution problem. But it's deconvolution by G tilde, which if you work out, will become a function like this, which is nothing but a complex Gaussian. And a complex Gaussian is the nicest function with which you can do deconvolution almost accurately. So you can project these visibilities, which are measured in that baseline grid, to that W project plane, which is this one. And now in between this and ILM is a Fourier transform relation. So you do all your Fourier transform and deconvolution between these. And you are doing it for each facet separately. So that is what Arnav was talking about, W project planes. So those are those facets. Different W project planes are different. If you wish, they are different facets. They are a little different, but I will not go into the details here. And if you want to do self-calibration, remember that your visibility changes. So this changes every time you apply again. You have to do all of this again, all over again. Well, so that is the basic idea of W projection. I have gone 6 minutes overboard, and I don't have anything more to tell you. This lecture from my point ends here. I'll take questions.
So while people are gathering their thoughts, may I ask a very naive question about W projection?
Yes.
So when do I know that, okay, I need to apply W projection? Means what is the limit?
Right. So you can actually calculate. So if you read the paper by, so Arnav showed a few pictures from the paper by Cornell. You can actually calculate how much error that you will, how much phase error that you will get. See, this is a phase, right? This term is a phase term.
Right.
So that gives you a phase error. You can, if you don't do it, you can consider this as a gain term.
Okay.
Right. So you'll get a phase error in your gain if you don't do W projection, and you can actually calculate how much that error will be. So depending on how much you require. So if you say that, okay, I will allow 10% of phase error, And for that, I don't need to do W projection, don't do it.
Okay.
Okay. Any other question?
Sir, up to first order, it is okay, but if we include higher orders, it would not be a Gaussian function, right?
Right, right. So that's a very
So
good
in
question. That's a very good question. That what happens if I need to include higher orders? So I actually have already told you the answer while talking about this. So can you tell me what is the answer? Can you guess? It's already there in your screen. See, I'm doing W projection with faceting, right? How small should I keep L square plus M square? Depends on, okay, so there is a little difference from this faceting and W projection. I did not want to go into the details. See, for every facet, you have one W projection plane, right? If I now choose more facets, which also mean that L square plus M square will be much smaller. So if you think that at this level of your faceting, so if you have divided your field of view into 3 facets, your L square plus M square is large enough that you need to keep the next term, break it into 6 facets. Then the next term will be even smaller. Got the point?
Yes, sir. Yes.
So you essentially
So we can extend to any other orders, right?
Right, right. You extend up to the largest W project plane, largest number of W project plane that you can do with your computer and satisfy you.
Okay, sir. Thank you.
Any other question?
Okay, I don't see any other questions or raised hands. So I would like to thank Professor Dutta from the school organizing committee to deliver this excellent set of lectures. I now, so just a
Yeah,
minute.
just a comment. The transcript of all the lectures apart from the lecture where we had internet glitch is all available in the Slack. I'll try to make a hand note for the lecture 3 also and make it available. So if you need, you can have a look. Okay, I'm done.
Right. Thanks. So thank you again. You can always like write back to him, or maybe you can communicate in Slack channel for further discussion and questions, comments, anything. So let us move on to our next tutorial session, which will be delivered by Shumit Choudhury. So Shumit, are you around?
Yes. Yeah. Let me share the screen. Yeah. Can you see my screen?
Yes.
This PDF. Yes. Okay. Let me presentation. Okay. So yeah. Am I audible?
Yes. You are.
Okay. So I think you have heard a lot of lectures about the 21 centimeter cosmology and all the basic things. Now I will talk about little bit about the